Hello, I am a salmon, and I'm going to tell you about how we actually make an EMF based on changing the magnetic flux. Then we will get to the ever-popular Faraday's law and Lenz's law, and then, just because we can, we'll solve some electromagnetic induction problems. Get ready for some sweet upstream swimming. Woo! Now, an important fact is this here, that whenever you have flux through a coil of wire, and whenever that flux changes, gets stronger or weaker in any way, you're going to induce an EMF, and current is going to flow around. So, for example, let's say you've got a coil of wire, and you've got a magnetic or a bagnetic field, as I like to call it. So call that, those X's are representing your B field. If that's just sitting there, no current flowing. However, if you make it stronger, you crank up the magnetic field, and let's say that suddenly you've got twice as much, more magnetic field, and that is going to make current flow around this coil in a certain direction. Later we'll talk about which way. Another example is, let's say you've got coils of wire. This is a side view. So, show this is a side view. And let's say that you've got a bar magnet. And this bar magnet is moved closer to it. That's going to increase the flux. You get an EMF. If you move it backwards, that's also a change in the flux. It's weakening it. Current's going to flow actually the opposite direction as it did before. If you take this magnet and you move it up, that's going to weaken the flux that's in that coil. Current flows. EMF is induced. You bring it back. That strengthens it. Current flows the other way. So anytime you get a change in flux, you get current flowing or an EMF induced. And hey, let me show you something else. I'm going to have to make myself bigger for this. Another way of changing the flux in a coil that's quite clever is, let's say you've got your coil and it's allowed to spin. And let's say there's a magnetic field coming through this coil this way. Lots of flux right now. If I just spin the coil, whoop, now if the flux is still going this way, no flux. Now I keep spinning it, lots of flux. Turn this way, no flux. Lots of flux. And every time you spin that, and you make the flux go up or down, you get changing flux, you get EMF, and you get current flowing. Clever, eh? So let's talk about Michael Faraday. He was a smart guy. He's credited with the Faraday cage. Protects you from static charges if you stand inside a metal box. It's kind of nice. But what he also gave us was Faraday's law. Let's put this up here. Boom. EMF is proportional to the rate of your flux change, magnetic flux change. And that's pretty easy to understand in equation form, where we can say that it's proportional to our change in flux over time. But then what we can also throw out here is this N for number of coils. So this E is our EMF, N would be the number of coils, and then this business here is going to be the rate of flux change. Now technically there is also, change colors here, a negative sign that you stick in here, but we're just going to be calculating the magnitude, so let's not be concerned about that. But the faster this flux changes, the more EMF you get. And what's also nice is if you can't change that flux fast enough, the number of coils that you get will also increase the amount of EMF that you get. Now, Lenz's law. This is a little bit trickier to understand and involves some weird right-hand stuff. But basically what Lenz's law says is this that you see here in writing, and also that magnetic coils are kind of like old people, and they hate change. And so, let's say the change we're concerned about is magnetic flux change. And we've got this coil that you see, oops, right here. Now, first of all, let's marvel at this coil drawing. Wow, that's a nice coil. And you've got a magnet that, if its north pole is here, you can think already that it's sending some magnetic flux down through this coil. Now, if you move that magnet closer to the coil, that's going to increase the amount of flux through that coil. And as you can probably guess, this coil is going to say, no, I don't like that. So it's going to try and fight that increase in flux by sending its own magnetic field lines out this way. And it's going to actually turn itself into an electromagnet with its own north pole that opposes the push of that magnet. Now, if that's the case, you can use what I call the second right-hand rule, the solenoid rule, and you can figure if it's going to have a north pole facing up, then the current is going to curl around a particular direction. In this case, we know that it must be curling around this way to make that north pole up. Now, in the opposite situation, if you had a magnet being pulled away, it's already going to be sending some flux lines through, but then it's going to weaken the amount of flux lines through. And you can guess that this magnet, again, is going to be sad. It's going to say, no, don't take away all my flux lines. So it's going to do all it can to send more flux lines through itself. It turns itself into the reverse electromagnet with a north pole down here. If you use that same right-hand rule, you'll figure if it's going to have a north pole down here, the current has to curl around a certain way, and that current must be opposite what we had the other way. And so the key of this is that coils will do whatever they can to fight a flux change. They'll turn themselves into an electromagnet to help fight that flux change. Here's an example problem. Why don't you pause it and see if you can solve it. Now here's what is going on for part A. You've got your field coming in, let's say, and your loop is, let's say it's this, is parallel to the field. Well, if they're parallel, then there's no flux lines going through it, and so there's no flux. So for part A, the amount of flux is 0. There's your flux. For part B, your loop is perpendicular. So let's say your magnetic field is coming in, your loop is like this, that's maximum flux. And so our equation for flux is going to equal BA times the cosine of theta. In this case, theta is, let's say, 0 degrees. And so that's going to make this equal to 1. You fill in for B, that's going to be 0.2 Tesla. For your area, 3 square centimeters converted to meters is going to be 3 times 10 to the negative 4th square meters. I'll let you work through that conversion on your own. Just take my word for it for now. And then we're going to end up with 6 times 10 to the negative 5th WB. Now that is the strange flux unit of Weber's or Weber's. I don't know. They also make grills, tasty grills. But that's our unit of flux. Now for part C, you've turned that loop from being perpendicular only 30 degrees. So you've got your same situation. You've got B, A. Now you've got the cosine of 30 degrees. Now this BA hasn't changed from before. That's still 6 times 10 to the negative 5th Webers. And the cosine of 30 degrees was 0.87, no, my bad, 0.866. And so clearly our flux has been reduced a little bit because now our loop's kind of at an angle to the field. And we're going to get a lesser value, something only like 5.2 times 10 to the negative 5th Webers. The end.